All right, so your homework's due Thursday, and we have a midterm exam on Thursday. And if you didn't already get your quiz, maybe you want to wait till later. I don't know. It's not great news for most people. It's okay news for some people, I suppose. Yeah. Welcome. Good morning. All right, so regarding that exam that we're going to have, you can prepare an equation sheet, and in fact you can have anything on it that you like, including you can put like examples or procedures on how to do things. It can be front and back, one page, but you're not going to be able to use it on the concept part of the exam. If you want a piece of bread, come on up, right here, fresh baked, just for you. All right, so the exam will be 75 minutes, 2 sections. It'll be concepts at the beginning, and it's you and your pencil and your brain for that section. And then for the problem solving, you need to bring your computer, and you can have anything printed on your help sheet that you'd like, but you can't start with pre-existing Excel files. And so if you use Excel to solve something, then it needs to be strictly from scratch. Any questions about that? All right. So the first thing we're going to do is watch a video that focuses on the movement of water through soil, just because I think that visualization of what we're modeling is really valuable. And I'm going to pause the recording here. If you're following along, here's the link that you'll need to go to. This way. So one of the figures that historically students have found so perplexing is this wetting front. So this is a graph that's showing the water content, and so as you're going down through the soil, over time that wetting front is making its way downward, but you don't go immediately from the ordinary moisture content to fully saturated. There's a curve here of the original moisture content to saturation, and so in this example, this first front, it has more moisture than it did before, but it's not fully saturated in the same way that a puddle at the surface in direct contact with the sand is fully saturated. And so today, one of the things we're going to be modeling using Excel is how quickly that wetting front progresses through the soil. And so this is maybe what a realistic model of the increase in water content looks like. You know, when it starts to rain at the surface, there is some depth that the water is fully saturated, but then you have a gradual a gradual decrease as you're going downward through the soil. What we're going to have to do in the Green-Ampt method is assume that there is like 100% saturation and then this limit between the initial water content in the soil. And that's just for ease of calculation, but it's a huge limitation compared to what really happens in the soil. So what we're going to try and say is, you know, here's this transition zone. We're going to say that, you know, the face of the transition zone is essentially flat, when in reality it's curved during a rainfall event. All right, let's finish watching this video. So after having watched that, let's just kind of refresh our memory of some definitions that were presented in the last class period. Porosity is the ratio of voids to the overall volume of some element, and within that void space there can be air-filled voids and there can be water that's in contact with the soil grains. Soil moisture content is the ratio of the volume of water to the total volume, and so then saturation is where you're saying how many of the voids are actually filled with water. So the ratio of the available moisture to the effective porosity. So the effective porosity is the difference between the total porosity and the initial, the residual moisture content after the soil is thoroughly drained, and so the effective porosity is how much actually increase in storage capacity there can be in a soil. Now, this change in moisture content is due to the capillary effect, and that's where, there's the existence of fine-grained voids that the water rises upward through, and so there's an increase in moisture content close to the water table, but then it decreases the further away you get because there's fewer and fewer interconnected small diameter voids that the water can rise in. And as it rains, we have this wave or a wetting front of increasing moisture content, and we've just seen those videos that kind of illustrate that wetting front. So during a rainfall event, the infiltration rate decreases over time, and modeling that decrease over time is one of the things that we're going to stab at today with the Green-Ampt method using Excel, is trying to find out over time how quickly has the wetting front made it down into the water. And the reason why the infiltration rate decreases is because there's a decrease in the internal pressure of the soil. As the water content goes up, the soil is, less thirsty is the way that you might think of it for additional water, and so the gradient or the driving force between infiltration, which is the difference between the initial moisture content and saturation, as that gradient decreases, so does the rate of infiltration. So here's that figure that I showed you before, where we have water at the surface that's progressing downward, and so far this figure is just assuming homogeneous soil conditions, and so things can really be different if you have different layers of soil, and the videos that we just watched make that point that it's one thing to have a continually perfect homogeneous sample of soil, but more commonly you'll have in one spot a little bit of sand, and another maybe a clod of clay, and there can be some decomposing roots in one spot that either increase or decrease the infiltration. So all of the things what we're doing today kind of assume a homogeneous matrix of soil. Now, in the Green-Ampt simplification, we assume continuous ponding at the surface. And so you can see there's a free pool of water here, and we assume that from the moment the rainfall begins, there's some ponding there, and it continues during the entire period that we're trying to calculate how much the length of the wetted zone has increased. And what we're doing is taking the Darcy relationship that we did a brief refresher example in class last time that says if you know the hydraulic conductivity of the soil and some cross-sectional area, and then we have the flux, the factor J, which is the difference in the heads relative to a distance, then that will tell you the flow rate through the soil. So taking that idea and extrapolating it down through the soil column, and we're thinking about what's the driving force, is the difference between the length of the soil and the initial suction head that's in the soil. This variable psi is a soil property that we can look up, the wetting front soil suction head. We'll look at some values in just a moment to see typically what those suction head values are for different types of clays and sands and so on. But we approximate the rate of infiltration, F, as the hydraulic conductivity, and then the ratio of the wetting front suction head to the length of the wetting front. Cumulative infiltration, on the other hand, is where we take that infiltration rate and integrate it over time. And so we know that the infiltration rate's always going to be changing, and specifically it's going to be declining, because the deeper this wetting front gets, the slower it's moving. The wetting front increases the fastest at the beginning of a storm because there's the most suction through the column at the beginning. But over time it decreases, and so we want to know sometimes the cumulative infiltration, just because over, let's say, a 1-hour storm, if we know the precipitation depth, then knowing the cumulative infiltration is going to be a big part of being able to predict what was the runoff quantity. Okay, so it's integrating the infiltration rate over time. And here's a figure that shows, number one, the declining rate of infiltration. That's this curve where we see at first the infiltration rate's relatively high, and it's getting shallower and shallower, and that slope is flattening out. until it reaches some minimum rate. And so that's the infiltration rate declining over time. And so the amount of infiltration, the total cumulative depth of infiltration increases quickly at first, and then it gradually tapers off. Rainfall excess is the amount of precipitation that's available for runoff. And so here for the infiltration rate, this lower curve, the rainfall hydrograph is telling us the precipitation rate. And so the units would be inches per hour or centimeters per hour. And so anything above this curve, anything above the curve of the infiltration rate is available for runoff. It's the rainfall excess. And it will do some other things before it actually runs off. It may have to wet soil surfaces. It may have to, if there is debris like leaves and twigs at the surface, it will have to wet all of those before there can be any horizontal movement. But the rainfall excess is what eventually is going to turn into runoff. So during this event, then the moisture content goes from the initial moisture content to full saturation. And so then the amount of infiltration would be the length, the penetration depth, and then the difference between the initial moisture content and the fully saturated porosity of the soil. So what we have to do is predict how long that penetration depth is at some time t. And so the Green-Ampt equation is what we're going to use. We'll set up an example in a spreadsheet just here in a moment to try and predict. And what we do to approximate that is we assume that we have ponding at the surface. And so here's the data that we have to try and identify for these calculations. One is the hydraulic conductivity of the soil. And we'll calculate this cumulative infiltration depth at various times. We have to know the soil suction head, and then we have to also know the increase in soil moisture during infiltration. And we can calculate that according to the porosity and the effective saturation. So here is the Green-Ampt equation in terms of infiltration depth, and here it is as a function of infiltration rate over time. So here's how you calculate delta theta. 1 minus the effective saturation multiplied by the effective porosity. So you'll be given these parameters at the beginning of a Green-Ampt problem, the soil characteristics, a certain time that we're interested in. And then you have to do an iterative method where you substitute a trial value on the right-hand side of this equation. And just as a beginning, what you can do is you could substitute in k times t, and then we calculate on the left-hand side the calculated value back into the right-hand side, because you'll notice here it's an implicit equation. We've got f of t on the left-hand side and on the right-hand side of the equation. So, implicit equation is one where the unknown exists on both sides of the equation. We can't solve it directly, and so we have to solve with iteration instead. So we've seen things like that before in hydraulics, and we just keep substituting until it converges. Now, a warning about convergence is in Excel, we've got goal-seek and solver. And you've used both, I think. Goal-seek, though, has a more relaxed convergence criteria built into it. So we need to use solver rather than goal-seek, or else we won't get accurate results. So just in the margins, be sure to remind yourself that we want to use solver and not goal-seek when we're doing Green-Ampt equation. So here's a table that's from your text that shows for different soil classes the typical midpoint values and then general ranges in things like the porosity, effective porosity, the soil suction head. And if we look at the hydraulic conductivity values here, we know that sand has the highest hydraulic conductivity, and water can flow really easy through it as long as there's a free surface in contact. But sand, as we saw in those videos, has the lowest soil suction head, and so it's not going to draw the water through the sand in the same way that we have these really high soil suction heads for loams and clays. So What you should keep in mind is the hydraulic conductivity decreases as you go from sand to clay, but the soil suction head increases as you go from sand to clay. Now let me ask you this sort of thought question here. Why is the effective porosity closer to porosity for sand than it is for clay? So look at the porosity and then the effective porosity here. So sand, we're talking about 0.437 is the porosity, and the effective is 0.417. Whereas for clay, the porosity and the effective porosity are relatively further apart. So what explains that difference? Do you remember what effective porosity is? It's a measure of, if you drain the soil, how much water is in the soil after gravity draining. And so you can think of it as, here in the clay, you've got a greater fraction of the water that won't drain out under the force of gravity compared to sand. In sand, the effective porosity is almost as large as the porosity because most of the water will drain out under the forces of gravity. But under clay, the effective porosity is lower, and it's quite a bit lower than the porosity because the clay continues to hold on to a fair amount of water under gravity drainage. Okay, so let's do an example here. Let's say that we have a silty clay soil that we looked up these soil properties for: the effective porosity, the soil suction head, the hydraulic conductivity. And we want to know the infiltration depth, which is capital F of T, and the infiltration rate, which is lowercase f of T, after 0.1 hours and 0.2 hours, assuming initial effective saturation of 20% and continuous ponding. So continuous ponding we have to assume in order to use this method at all. As for the initial effective saturation of 20%, then we need that in order to calculate the delta theta. All right, so let's start with Excel here and put in the information that we've got. The effective porosity from the soil table, you know, we get these values from table 7.4.1. So the effective porosity is let me leave this up so you can start to mimic its organization. The effective porosity in fact, I'll pause and give you a time to kind of create all these spaces where we're going to be putting in information. You may not necessarily need to type in the explanations and the formulas, but I'll give you a moment to do the rest. All right, so the effective porosity, that was specified in the example as 0.423. The suction head was also a given just based on the fact of what kind of soil it was, 29.22. The K, the hydraulic conductivity, 0.05. And the S sub E, 0.2. So now we need to calculate the delta theta using this formula. So 1 minus S sub E, oops, what do I do here? 1 minus S sub E times the effective porosity. All right, so now the procedure here, we want to know at 0.1 hours the infiltration depth and the infiltration rate. So we have to calculate first the infiltration depth, and then we can use that to find the infiltration rate. So here's the formula that we're going to try typing in. So do the whole formula here. Equals K times T. And I'm going to anchor that because I want to be able to drag it down later on. So any reference up here into the constants we want to be sure to anchor. Psi times delta theta times the logarithm plus. We have to actually have this guess value for it to reference, and so let's use k times t as our first guess value. So k times t, k times t. All right. So I'll do the right-hand side here. Again, k times t. E10 divided by suction head all right, let's just see what we got here. So k times t plus sine so there's going to be a difference between the right-hand side and the left-hand side. So we're not converged yet. And this was just a guess value, but we are going to change this guess value. So I'm just going to, now instead of it being a formula, I'm going to type in an actual number because Solver can't change it unless it's an actual number rather than a formula. So I'm going to change it to 0.005, which it calculated before. And then let's go to data, what if analysis. Solver's not installed here, so I'm going to have to install that, I think. Oh, let's see, options maybe? There we go, Solver. It's referring to this f of t that's just sort of a guess value. And so I'm typing in the formula, like the right-hand side of this formula in C10, and then where it's referring to f of t, I refer it to B10, which is my guess value. And this initial guess value was k times t. So let me put it back on the formula. And hopefully you brought your binoculars because that's awfully small up at the top. The idea is any reference up here to the soil properties, anchor it because we're going to drag it down. But the time in question is the 0.1 hours. Okay, so using these initial parameters, you should have 0.010 for the right-hand side, and then there will be some difference between the two. And then what we do with Solver, oh, there it is, Solver, we want the difference to be 0. So our objective is the difference should be 0 by changing this guess value, and then we solve. And we could, if we want, double check and see the precision. That's good enough precision for us. The Solver's default value is fine. Okay, so solve. All right. So it should be 0.318 centimeters is the total depth of infiltration after 0.1 hours. Let me pause. All right, so now once we get the infiltration depth, we can use that to calculate the infiltration rate. So it is K times psi times delta theta divided by the infiltration rate plus 1. All right, so that's at that specific instant in time, the infiltration rate. This isn't the infiltration rate average over the period. That's the infiltration rate right at 0.1 hours. So this infiltration depth is the cumulative amount that's happened during that period. So now we also want to know at 0.2 hours. And so then all we have to do is have some guess value point. Our infiltration depth would probably be higher, so we could say maybe 0.4, just as a starting point. And drag the, all the other formulas down. Oops, it's going to. So drag these formulas down, and what we're going to have to do is use solver again to optimize the difference between the right-hand side and the left-hand side of the equation, where the left-hand side is the guess. So our objective is for the difference to be equal to 0 by changing the guess of the actual depth. And solve. Let's see what that guy gave us here. Something's not right. I must have not anchored one of the references correctly here. Oh, it didn't solve all the way. I don't. All right, so the difference should be 0 by changing that. Okay, that's right. I think I had it set to this difference being 0 rather than the next one down. Okay, so then at 0.2 hours, our cumulative infiltration depth is 0.451, and the infiltration rate decreased. Who can conceptually explain why does the infiltration rate at 0.2 hours look so much lower than the infiltration rate at 0.1 hours? Why did it decrease? Right. There's less suction because if we go back to the figure of the wetting front, when we have when the wetting front depth is deeper, remember, as soon as the water is saturated, then that suction has been satisfied. And so there's some soil beneath it that's still drawing the water downward, but the majority of the column has already been saturated with water, and so the infiltration rate declines. So we're trying to model the curve of both of these using the Green-Ampt method. Any questions on the spreadsheet or persistent errors we want to take a look at before we move on? All right. Now, Green-Ampt assumes continuous ponding. But the ironic thing is we can use Green-Ampt to calculate how long it takes for ponding to actually occur, because ponding won't be instantaneous. Ponding has to be when the rainfall rate is greater than the infiltration rate. So here's a curve that really is important, this figure that just came up. And what it's showing is the potential infiltration rate is decreasing over time for the reasons we just discussed. If we assume that rainfall rate is constant, then there has to be some period where we're not going to actually have enough rainfall to completely satisfy this potential infiltration rate. So the actual infiltration rate is limited to the rainfall rate to begin with, and then once the rainfall rate is greater than the infiltration rate, then ponding is going to occur. So if we look at it a different way in terms of the cumulative amount, the time to ponding is where you have the cumulative rainfall, that slope, intersecting the cumulative infiltration. So we can calculate the T sub P with this formula. if we know the rainfall intensity and the hydraulic conductivity, we can calculate the time to ponding. And so in this example, let's say that we have a soil with an initial effective saturation of 45%, then we can calculate the delta theta with this formula. Delta theta is 1 minus S sub E times theta sub E. And so what I'd like you to do is calculate, for a rainfall intensity of 1.5 centimeters per hour, how long is it until ponding occurs using this formula? What gets a little bit more tricky is to find out to solve for an unknown rainfall intensity rather than solving for the time to ponding. And we'll work on B and C together, but for now just solve part A. Did anybody else calculate 0.156 hours as the time to ponding? Okay, so the delta theta needs to be 0.2326, and we have an I of 1.5 centimeters per hour. That's the rainfall intensity. Let's see, I haven't actually looked that closely at the units before. So we've got centimeters squared per hour here, and centimeters squared per hour there, and it's also another hour, so yeah, I think it does work out to hours. All right, so the time to ponding will be 9.4 minutes. Now, the next part of this says what rainfall intensity would cause ponding after 20 minutes. And so the approach there is just to rearrange the equation to solve for I. And we can get the roots of that. You know, we have, this is a series of soil properties that becomes a constant that we put into this equation. And if we solve for the roots, then we have a negative root and a positive root. Now obviously the rainfall intensity is going to be the positive root. And it makes sense that if the first example was 9 minutes based on an intensity of 1.5 centimeters per hour, we're saying what rainfall intensity would cause ponding after 20 minutes. And so it's going to have to be a lower intensity. And it turns out to fit our expectations here, about 1.04 centimeters per hour if we rearrange that equation and solve for I. Now the last question, we would actually need the computer to solve how much cumulative infiltration during the period from 0 to 0.156 hours, the cumulative infiltration depth. And so I want to show you what I did for that one. For ponding time, here are the here's the storm with an intensity of 1.5 centimeters per hour. We want to know the cumulative infiltration, and so here's the properties that were specified in the problem statement here. And we want to know basically the capital F of t at a certain time. So we have to do the same starting with the guess value, and if we just delete both of these because we don't start by knowing, but let's say we assume maybe 0.1 is our infiltration depth, centimeters is the units there, and so then we have to do the formula for the infiltration depth. It's going to be K times T plus psi times delta theta times the logarithm of 1 plus f of t, where we use our guess, divided by psi divided by delta theta. Okay, and we have some difference, and so we have to use solver to minimize that difference down to 0. So it is set for the difference to be 0 by changing our guess value. And we let it run its course. And it's saying that the total infiltration amount would be 0.331. So this was asking how much infiltration is there during the period that it takes to get to ponding. So this value of 0.156 hours, that was the answer to part A. So we can find the cumulative infiltration depth until there's ponding there. So I hope that will put you on the right course for the homework. There is one more thing that's included in the homework, and that's a really easy way to estimate the shape of the curve. Rather than looking at some of the fundamentals like the soil suction head and the hydraulic conductivity, the Horton model uses a different approach. It just does curve fitting based on some experiments with different types of sand that have been taken into the lab, and they measured the infiltration rate physically over time, and they found a couple of ways using an exponential function to, depending on what soil type you've got, to estimate F sub P, where F sub P is the potential infiltration rate and it's declining over time, and so there's a minimum infiltration rate. This F sub C is this value here that it never goes lower than F sub C. And the initial infiltration rate, F naught, at the beginning is where we start. Once it's decreasing because some of the soil suction has been satisfied, then we use this exponential function to the difference between the two. The gradient is the declining driving force. So the Horton model, I think you've got one homework problem that's related to just looking up what kind of soil type you've got, looking up these empirical parameters and substituting it into that equation. So we've still got a little bit of time. Let's do that Horton example here. Let's say that we have an infiltration rate, we want to know after 15 minutes, if we've got rain of 300 millimeters per hour, then for a Leefield loamy sand, what is the infiltration rate after 15 minutes? So you'll notice that the K value here is already in terms of minutes, and so you don't need to convert the time into hours because we want K times T to be unitless. So let me pause for a moment so you can substitute those values in to find the infiltration rate after 15 minutes. For a Leefield loamy sand, then the F naught is going to be 288 millimeters per hour. The F sub C is 44 millimeters per hour. And the K value is 0.13 minutes to the minus 1. So then F sub P is going to be 44 millimeters per hour plus 288 minus 44 e to the minus 15 times 0.13. So I think when we substitute all that in, it should be 78.7 millimeters per hour. Anybody else get that same value? All right. So it's just kind of an easy approximation. The key to using it is whether or not the soil has been characterized that you actually have in a certain location of interest. All right, so let's just take a look at the announcements here. The main thing on your plate, of course, is the fact that we've got the exam on Thursday. I'd encourage you to refresh in your mind some of those concepts, because it seems like people are doing pretty good on problem solving and pretty good on like setting things up on the computer, but then sometimes struggling to explain the underlying concepts. And so my suggestion is, although that's a smaller fraction of the points than problem solving, because it's the part that a lot of people are struggling on, maybe emphasize your understanding of the concepts before the exam. Let me know if you have any questions on the homework. Otherwise, just be sure that you upload that to MU Online before class on Thursday. We'll see you then.